Hi guys, so here's the next video for the same. I'm not going to go in much of a detail, but I'll just show you the pages. I'll just show you the formulas or the shortcuts I have written. You can obviously pause the video and you can note it down accordingly. See, this is actually I have taken because you have to know the strong field ligand and the weak field ligand. So you must know that the water, including water and above, is going to be weak field ligand according to this table, and the below that is going to be the strong field. And you must remember carbon monoxide, cyanide and nitrite are the one which are very most, even though you have to remember, like you can, even if you superficially see it's okay, but you must remember carbon monoxide, cyanide, nitrite, and some common ammonia, pyridine you have to remember. Also you must remember that water is the weak field ligand, then fluoride, then above chloride. So in the halogen table, if you'll see in the group wise, first it comes fluoride and then it comes chloride, then it comes bromide, then comes iodide. Iodide is the weakest ligand field, so you can remember accordingly. You can always pause this and you can see what's going on. And even if you don't understand this particular table I have taken from Wikipedia, and this is how we calculate the oxidation number. This is also an important formula, so you must remember oxidation number, how you're gonna count. This is a little example I have given, so you can note it down. Okay, second thing is magnetic moment. This they might ask, so you must go through this formula once. N is the number of unpaired electron, because obviously we will see the magnetic moment only on those which has unpaired electrons. And this is general thing which I have noticed, or many have noticed actually, that if n is equal to 1, that is if you have one unpaired electrons, your magnetic moment will somewhere come around 1.9. This is just a trick, just in case if they have given you magnetic moment and they are trying to ask you what is the unpaired electrons, you must calculate it first like this, and just to track back, you should kind of know that if it's given a magnetic moment as 1.9, then somewhere your unpaired electron will be around 1. Similarly, if it's given 4.9, then it might be 4. I'm not saying that you rely on this like exclusively. You must calculate like this, but then again you can track it back. Now again, crystal field splitting is an important part, which will definitely, if not one, two questions might come. So you must understand what is happening and see in crystal field splitting, it's basically talking about, wait, I'll just, at least you can note it down. See, I'm not going to go in detail like what is happening or what is not happening, but I'll just tell you a superficial idea. This is the theory part, and this is not this, but this two are the very important formula. This sometime they will give you pairing energy, but mostly it is this. So I'll tell you what is happening here, right? Crystal field splitting, it's like splitting in the d orbitals. D orbitals is 5 orbitals are there, 1 2 3 4 5. Splitting due to the ligand is the main thing which they are trying to depict. Okay, so there are that there could be octahedral, there could be non-plane square planar, there could be tetrahedral, there could be octahedral, but these two are the most common. Mostly it would be octahedral mostly. So first of all, you have a geometry, octahedral or tetrahedral. Now you will see. So for example, I'll tell you what happens when there's something like coordination compound will come and they will ask you CFSC or whatever. So the first thing you will note down is, does it have uh, what do we say, coordinate number as 6, that is, nh6 for say example. It's not exactly what it is, but let's say ab6. So if it's 6, it means it is going to have an octahedral complex. So once you determine if it's an octahedral or tetrahedral, now you have to see if the field, the ligand field, is strong or weak. So for that you have to remember at least some of the things. You can just superficially go. So once you know that, you must know that if the ligand is a strong field, then splitting will be high. So when you will fill up the electrons, you will fill this half paired, then half paired, again you will pair this up, then only you will go there, because the splitting is high, energy is very high between them. So they might not be able to cross this energy, so they will pair up here. After that, they do not have any chance, they do not have any space, so obviously they will go upside to further pair up, to further fill the electron orbitals. But in case if it's a weak field ligand, the splitting is not much. So in this case, the pairing is like this: 1 2 3, then 4 5, then 6 7 8, then 9 10. So you can, normally how you pair here, you can pair here as well. But you should remember, in crystal field splitting strong, if it is strong, it's going to be, that happens only in the octahedral complex. The strong field, there will be high splitting. But when you go to the tetrahedral complex, this is actually, in tetrahedral complex, both will be same. It's usually act as a weak filled ligand. Okay, so you should remember also in this, you should remember this formula, because you should note down in the question. Sometime they will ask you, give us the CSFE, and they will say in this, they might give you tetrahedral complexes, and they will ask you, give us the CFSE in this. So first you calculate tetrahedral CFSE, and then you convert it through this formula into this, right? And in 1 mark question, if they ask, so the splitting of tetrahedral complexes is somewhere around 45% of octahedral splitting. Okay, and I really want to, but I do not have time. But see, in d orbital we have dxy, dyz, dzx, dx square minus y square, dz square. So there's like there is axial symmetry or something. So when octahedral complexes come, they will, most of them, the repulsion is more on the one which is on the axis, and that's why on the axis only we have dx square minus y square and dz square. That's why these are going so much up, because there's high repulsion. That's why it's going. And the other one which are not on axis are dxy, xz, and zx. Okay, as you can see here, these are like this, and they are exactly on the axis. And when you see the octahedral complexes, they are like, two of them are going to be exactly repulsing in the repulsion for each other, and the other are like not that repulsion. This is obviously more repulsion, more energy. This is energy diagram, this is going like this, energy above. So more repulsion, more energy. But in the tetrahedral, what happens, and when you'll see the tetrahedral geometry, most of are on not of the axis. So obviously the two which are on axis, which will have a less repulsion, and most of the tetrahedral part are not on axis. So obviously these three who are not on axis, in case of d orbital, they will have more repulsion. Even if I'm not able to make you understand this, but most important thing is you should remember this formula. If it's given octahedral complexes, you see if it's strong filled or weak filled ligands, because when you see here, this is a strong field and this is weak field. What happens in strong field is that the energy distance between the two is this is the Barry center, and above this is 3/5, and below this is 2/5, right? So see, in this octahedral complex, the most important thing is you have to focus on the pairing of electrons. Like for example, crystal split split is too much, you will obviously push the electrons first here all and then here. But if it's weak, like normal how you fill, half 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 half, then pair 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 pair. Okay, so that's how you do. So depending on the number of electrons, the formula is going to be this only. Remember, the one because this means crystal field splitting energy, right? Like the energy which is trying to, not splitting, sorry, it's stabilization energy, the energy which is trying to stabilize it, right? See, minus 2, where is it, 2 by 5, this actually doesn't have energy. This is the what which is increasing, the one which is increasing is going to stabilize, right? So what we do overall, this is going to stabilize, but at the same time this stupid person is going to take that energy off. So what happens is you have this you have plus sign for this and you have negative sign for this. So that's why you will add up the energy which is coming inside, you add up, and the energy which is going below, there's no energy, so obviously you will delete it out. So 3 by 5 into number of electrons on those, that is neg, and remember that upper side is eg and this is t2g. In case of this, it's not gg, it's t2 and e, right? So wherever t2, you should remember this, it's 2 by 5, t2g is 2 by 5. Where is it? Yeah, so you can remember this. In case of octahedral, it's this, right? And in case of tetrahedral, yeah, tetrahedral is basically the same, because it's in tetrahedral this thing is inverted. See, in that the T2G was below and EG was right, and that's this, in this it has been inverted because of the axial region and repulsion region. So you have to remember, in EG this is the same way you will do. See, 2 by 5, this time it will be plus because the energy is in that. This time below is minus 3 by 5, that's why we will where is it, we will subtract that, right? Make sure you calculate the number of electrons properly. So this is a very important thing. Now we come to the chemical equilibrium. There are a lot of formulas in this. Okay, wait, I hope you should see in, there's something called colligative properties, in which we have 4 things. First is vapor pressure lowering. Like for example, there's a pure solution, and then there is a solution, there is a pure solvent, and then there is a solution in which you have added some solvent. So how much the vapor pressure is getting lowered is what it is being asked. Similarly, we have boiling point elevation, like the same way. So there is some let's say there is some pure solvent, you added some solute, it becomes solution. So there will be changes, there will be lowering of vapor pressure, there will be elevation of boiling point, there will be depression of freezing point, and there will be some osmotic pressure. The same formula is there. You must remember, see, this is the mole fraction. What they're saying is this is the pure solvent, this is the pure solvent, yeah, this is the solution, this is what's saying relative lowering, this is relative lowering. Okay, so how much is lowering? It is equal to the mole fraction of the solute, right? So what they say, in the diluted solution, this N2 is what, small, N2 will be very small. Diluted means more water, solute is less, so we are considering is it very less, so we are just ignoring it here. Okay, mostly they will ask this formula, so I want you to remember this. This is going to be relative vapor pressure lowering. It's equal to, see, N2 is what, mole, right? So mole is equal to weight of the solute used per molar mass of the solute. For example, it is given glucose or something, so weight they will be giving you, then you have to calculate molar mass. Obviously, by you must know what is the mass number for C, what is the mass number for O, and what is the mass number for H. You will calculate this by yourself, or they might give you, depends, and this they will definitely give you. And solvent, water molar mass of the solvent, depending on what solvent it is, and then the weight of the this formula you must remember, right? So example, if moles, only moles is given, it's going to be very simple. Simply put the moles of the solute per the moles of the solvent. If it's going to give you weight, you have to do it like this, right? Sometimes maybe in 1 marks they might give you only mole fraction, you do not even have to worry. So you put the solvents, vapor pressure of the solvent, this is pressure, and you will quickly get the calculation. Similarly, boiling point elevation. See, boiling point elevation, this is the simple formula, that is the change in temperature, right? See, for example, you have to remember this will be going to be in the plus. So here also it's going to be in F. So if it's depression, right, it got lessened, so we were going to minus it from the pure one. If it got elevated, we are going to minus it from the the elevated one, the second one, that is the solution, not the solvent. Okay, so delta TB is equal to Kb into m. M is what? Molality. Here it was mole fraction. Here it is molality. Molality is what? Moles of solute per kg of solvent, right? So Kb they might give you, obviously they should give you. Okay, so this, in case direct molality is given, that's a very rare chance they will give you. Maybe they will give you in 1 mark question, but there is very good chance they will give you this. So remember this. See, this is almost like this only, almost like this, but only the constant has come up, and this side it was relative lowering. This side it's only simply the new temperature minus the uh, older temperature. Okay, so you can remember it like this. Here also it's exactly same, just the constant is different. Okay, and you must remember here M1 you have to calculate, or it might be given. Here it's simply 1000. Why? Because molality is something which we do per kg of solvent. It's already a constant, it's already a standard thing, right? So the moles of solute per kg of solvent, we already know what is the solvent all about. So it's going to be similarly, see, W2 by M2, W2 by M2 into 1000 by W1. Instead of M1 we have 1000 here, so you can remember it like this. And similarly this is this delta F Kf into this. Okay, I'll just pause it up a little bit. I'll just focus so that you can write down the formula at least. Okay, wait. I hope it's clear to you. This is osmotic pressure development. See, this is exactly like PV equals to nR2. Why? Because here we are talking about molarity. V is going to be in liter 1 liter. So obviously even if you write or do not write, it's the same. So it's like, even if it's, I have written P equals to CST because this is what we call solute constant, which is going to be the gas constant. For example, so in question they have given you some osmotic pressure or something, and they're asking you what other pressure or something, and given you R, it means that this going to be this. But yeah, it's going to be this question only. So you have to remember like this: pi equals to CST. C is nothing but concentration. Sorry, this is molarity. So you have to calculate the molarity. Remember, molarity is equal to mole per 1 liter volume. Okay, so it's similarly like PV equals to nRT. V is going to be 1, so it's not visible. N is nothing but the concentration, because the V has gone here, so you remember it like this. And T is the temperature. It will be, you make sure you remember the unit, make sure you are pretty much clear about the units what you're going to use. Okay, depending on R. And I would suggest you, whenever you're trying to solve the question, don't only write the magnitude, always and always write the what do we say, unit along with it, so it will be easy for you to calculate accordingly. Okay, see, in pure solvent it was 0, but after you added solute there is some osmotic pressure, and that's what we are calculating it here. Okay, an ionic equilibrium. In ionic equilibrium, see, strong acid is going to properly dissociate, like strongly everything will be dissociated. But in case of weak acid, and usually they will ask you ionic, they will ask you the equilibrium constant whatever for usually weak acid, right? So if they have given you dissociation constant and they are asking you, tell me the degree of dissociation, they will definitely give you the concentration of the compound. You will directly calculate it like this. So degree of dissociation is under root of dissociant constant by the concentration of compound. On what? Molarity. Concentration of compound is going to be molarity. Remember, molarity is mole per liter, per 1 liter. So you have to make sure it's like that. Also Ostwald's dilution law, it says, as you can see here, alpha is inversely proportional to concentration in this formula, right? Inversely, and concentration is inversely proportional to dilution. Obviously there is a solvent, so there is a water, right? There's a water, it's dilute, you are adding the solute, you are increasing the concentration, the dilution is decreasing. Now equilibrium constant, for many of the, and also equilibrium constant is given, first you write down the reaction, and make sure you ignore the solid one, because there is no change in the solid one. That's why that will not come under the equilibration constant. There are three ways: either you get it from the molarity, or you get it from the partial pressure, or you get it from the mole fraction, depending on what they are asking and what they have given you. It's nothing but simply what is in the product, you will write it there, and what is their mole given, you will write as the power divided by what is in the what do we say, what is in this left hand side. You will write it in denominator and simultaneously the power. Similarly, it's all similar, right? So depending on the partial pressure given and whatnot, what you have to remember here, see, this is also similar. Only what thing you have to remember, the relation between kp and kp and kc. Yeah, so you do not have to fear much if they are asking you kp. It's nothing similarly like kc, just that the partial pressure is there. Okay, and usually this partial pressure thing is done in the closed vessel. So the relations of kp is equal to kc. You do not have to again worry rt delta n, right? So delta n is nothing but plus how many moles are there, m plus n, minus how many moles are in reactant side, x plus y. You just minus it like this, as I have shown. And also you should not do it for solid, because we are talking about gas, right? We are talking about gas, we hardly have to do. So just in case delta n both sides are equal, then kp becomes equals to kc, right? Obviously when this becomes 0, this becomes 1. Similarly, kp has a relationship with kx as well. This time it's going to be kx P total delta n. So here it was RT delta n. Here it's total P delta n, right? Now what is this? pH, it's very simple. Just in case if they have given this, very rare chance they'll give you, but just in case they have given you concentration of H0 plus or H plus, okay, you just have to get the negative log of that and you'll get the pH, right? See, in strong acid there's dissociation full. In weak acid you have to be careful about the alpha, right? And always you have to remember this: for the water, the concentration for both of them is 10 to the power minus 14 m square. So H3O plus is always going to be 10 to the minus 7, and OH minus also. So that's why the pH of the water is 7 always. Okay. So what you have to notice here, for example, something is there, you dissolved it in water. Now it's being asked what is the pH. Okay. First of all, they will definitely give you what is the concentration of some solute which they have given. If it's going to be strong solute, you do not have to worry again, right? Just have to see what is the concentration. For example, if it's alpha, sorry, not alpha, if it's given 2 mole of some concentration and it's going here, so it's strongly dissociating. So whatever x or y will be coming, that will also be 2, 2. It's a very naive example. Obviously, this is not going to be 2 or something, but for example, let's say HCl is given in 10 to the power minus 7 concentration, and when you're making the reaction it will become H plus and Cl minus. So H plus is also going to be 10 minus 7. Okay, I remember that. And another thing you have to remember is, if your concentration is coming very much greater than 10 minus 7, you can ignore the water, because H3H, when you are dissolving HCl in H2O, remember H plus is not only coming from HCl but also coming from the H2O, so you have to add up both, right? So when you do not need to add up, when your HCl's H plus is going to be greater than 10 minus 7, obviously even if you add up it doesn't make much difference, so you can ignore that. But if it's going to be less than or equal to 10 to the minus, never ever ignores, because what you have to make sure, if it's asking you pH for the acid, it has to come below 7 or somewhere equal 7, right? If it's asked about base, so it's going to be 7 and above, so you can trace back like that. So for strong acid there's not much confusion. For weak acid, they might give you 10% compound is dissociated, that is, so this is how it dissociates, right? Some solute is there. When they dissociate in case of weak acid, C alpha is going to be lessened from the one which we have dropped, so only C alpha has been dissociated. C alpha, they will give you alpha, Even if they haven't given you alpha, they might give you Ka and C, which you have to then calculate alpha as this. Okay, and again you have to be careful about that. You always add the H waters depending on if it's going to be more than 10 to the minus 7 or not. You can ignore it accordingly. Now buffers. How do we get the buffer? There is acidic buffer, there is basic buffer. Acidic buffer, we add the weak acids, right? And obviously the conjugate of weak acid is what? Strong base. And that strong base is salt. For example, HCl is there. No, not HCl. CH3COH is there, is a weak acid. What would be its conjugate base? CH3COO minus. So for that base we make a salt. This is the salt, and then we add up and make the buffer. Similarly, if weak base is there, I don't remember the exact what do we say, example for weak base, maybe it's NH4OH, but then you know, it's all about the conjugates thing. What we are talking about, the conjugates here. So that's why, see, your buffer has to have that acid. For example, I told you CH3COH, then the salt is going to be CH3CO something. For example, here it's NH4OH, then your conjugate acid has have to be NH4 something, right? It has to be similar. For acidic buffer, if they want you to give the pH, you have to give pKa, acidic buffer, because we are using weak acid. Okay, so you have to give acidic for pH equals to pK plus log salt by acid. You may note it down. I'm not going to waste much time of you. Okay, for basic effort, similarly, the same thing, everything is same, just instead of pK it's pKb, but make sure this is pH you are calculating, this is POH you are calculating, because if it's basic buffer, we're not going to get H plus, we're going to get OH. So obviously they will ask you pH. That's a twisted question. How do you get it? You get it like this. You get the POH and you keep it in here, and then you get the pH. Okay, now hydrolysis of salt is a very interesting thing. Salt could be, wait, uh, salts could be acidic, basic, neutral, or neutral, yeah, but these two neutrals are different, because if its salt is acidic, we are using strong acid and weak base. And remember, this is not acidic because of strong acid, because when we are making the salt inside the solution, it's not going to be this strong acid as acid. It will become its conjugate base. It will dissociate, right? So the conjugate base of strong acid will be weak. Okay, so the weak acid will not show much, will not be able to displace water. But if we have weak base, the conjugates will be strong acid, and that is one which is showing the nature in the salt. And similarly others. See, I'm not going to waste much time, but I'll just show you this and you can note it down. I hope it's clear. Similarly, solubility product is there. I'm really sorry, but I'm not able to explain much, because seems like I should have uploaded it way before, but even I was occupied. See, the question type I could tell you, maybe they will ask you, says calculate the solubility of something in pure water, right? Solubility product is of something where you cannot add any ions further, right? It's become saturated. That's what a solubility product is all about, right? It dissolved, it's saturated, you cannot add more. If the compound is giving you AB, see, I really want to explain you, but I have got really less time. You have to remember this. If they ask you solubility for a certain compound, you have to remember, okay, AB x square, AB2, it's going to be x into 2x square. You have to write first the balance equation. See, I've told you this question. Somebody is asking you calculate the solubility of something in pure water, right? Simply write the equation, how it's going to dissociate, balance it, depending upon ratio of product, calculate the solubility. For example, here is AgBr. So you make the balance equation Ag plus Br. So this equation is balanced because Ag is 1, Ag is 1 here, Br is 1, Br is 1 here. You make the KSP as x square because the ratio is 1:1. If it would have been ratio as 1:2, you will have to do x into 2x square. If it would have been ratio as 1:3x, it would have been like this. So calculate is very simple. Now, mostly there's a very high chance they will ask you solubility in certain other solution. For example, I'll give you the example here. You note it down what you have to do. For example, AgBr solubility NaBr. You have to look out for the common ion because there has to have the common ion, right? So already something is there. NaBr is already a solution. It means Br plus must be already there. So you do not again have to worry. What you have to do, the solubility, what would have been the solubility for this? And then add it like this. So for example, AgBr will have y for Ag into y plus something of this. They will give you this. And sometimes they will ask you in 2 marks question or 1 marks, which of the given option your compound will be most soluble to. Look for the water. If it's there, most soluble. Now, does it has common ion? If it doesn't have common ion, it doesn't really matter. Again, it will be soluble according to him. So most soluble. Then if it does not have common ion, that will be the second one. After that, if it has common ion, look for the concentration. If it's going to be the most concentration of that common ion, least soluble. Obviously somebody has already occupied the room, you're going to get the least spaces. Okay, now precipitation of an ionic compound. Whenever ionic product is greater than solubility product, then you will know that it will precipitate. They will give you KSP and then you can calculate of the solubility of that according to this equations. You have given solubility and you can calculate solubility. Solubility is like X. And once you get the solubility, you will keep it side and then you will calculate the given solution's concentration. You will get the ionic product. Just to note it down, okay? Selective precipitation is like, you have given two solution and you want to precipitate it like one by one. You do not want them to be precipitated at the same time. You just read it out, try to understand what is happening. I have given you examples as well, I hope. And one more thing I want you to notice, that's very basic thing. Here you might get confused sometimes if 10 minus 8 is equal or 10 minus 6 is greater or something. Remember, the more negative it is, the more less or the more smaller it is. Okay, I hope it's clear. In case any doubt, just comment down below. We only have one day, I know, but at least I can help future people. See, I'm going to do it as fast as I could because you can always pause and you can note it down. Now I have come to electrochemistry. For EMF, you have to make sure that reduction potential is going to be at cathode, it's going to be RHS. They might give you the cell, so you have to see the cell. This is LHS, this is RHS. The RHS well will come in the front and the LHS valve will go here. And make sure EMF is going to be always positive. Okay, if it's not positive, you must have done something wrong. See, this is the cell. They will show you this is a salt bridge, and this is RHS, this is LHS. RHS is cathode. That's not the case in electrochemical cell. I think this is galvanic cell. In galvanic cell, cathode is plus, but in electrochemical cell, the electrodes could, the cathode would be negative. Yes, they might ask you in the 1 mark question that which element will replace or displace it. So you should draw this. Okay, Nernst equation, that was the what we saw here is something with the standard condition. Standard condition is temperature is 25 degrees Celsius or 298, concentration 1 molar, pressure 1 bar. Sometimes they will give you the cell, and they will put the concentration whatever. The moment you see the concentration is not 1 molar, the moment you see pressure is not 1 bar, mostly they will give you the same temperature, but just in case temperature is also not there, this is the main formula. This is the standard potential. They will give you the standard potential minus 2.303 RT by NF log Q. Log Q is nothing. You have to just write the balanced equation, which I haven't written. So write the balanced equation, that reduction, which one is going for reduction, which one is going for oxidation, and do it accordingly. Mostly they will give you the temperature same, so you can remember this formula, 0.0591 when n is what number of electrons consumed. So that's why I'm saying that the reaction should be really balanced. And log Q is nothing but just like a Kc, you could say, reaction coefficient. Okay, that's how you calculate. And this is the equilibrium, just in case if they've been given you EMF of cell or something and they're asking for the equilibrium constant, you can also get it like this. This is when temperature is not equal to 298 Kelvin. This is when temperature is equal to standard temperature. Conductance is this. Sometimes they will give you cell constant, which is called L by A is a cell constant. So in that way, if they have given you cell constant, you have to do it like this into 1 by X, because then only it will become like this. So this is standard formula. Just in case they haven't given you cell constant, you will do it like this. This is molar conductivity, this is equivalent conductivity. Molar conductivity, we are talking about polarity. In equivalent, we are talking about normality. And what is the effect of dilution on both? All the things are directly proportional except the specific conductance, because specific conductance is very much specific about little place. So if you increase the dilution, there will be less ions in that specific place. That's why it's inversely proportional. But also remember, in case of conductance, strong acid will be increased, okay, but weak will be more increased because of the Ostwald dilution. The more dilution, the more dissociation, and the more ions means more conductance. This is an important things. See, for the strong acid, you can easily calculate maximum molar conductance. From this graph, this is going to be the maximum molar conductance for strong, but for weak, the graph usually comes like this. It becomes very difficult, right? So for that, we have come up with the Colruy's law. Colruy's law is very basic, very easy, I would say. So for example, CH3COH, and they're asking you, tell me the given weak electrolyte and 2 strong electrolytes. Find this for the weak one. It could be like, see, there are different way of saying this. I don't know if I've written infinite dilution law or zero concentration. Yeah, molar conductance, infinite dilution, because we can also say it like this, or molar conductance at zero concentration, we can also say, right? So this is this. So for weak it is given. Try to find, for example, I haven't written the example. For example, it's given CH3COH, and they will give you certain strong electrolytes, this thing. So what you have to know is which strong electrolyte has CH3COO. Obviously, you know what, I'm just going to give you the example. CH3COOH is there, then HCl is given, and CH3COOH CONA is there, right? And then NaCl will be also given. So how are you going to get this? CH2 you will get from this one, this you will get from this one, because these both are strong, right? So you will add those, strong one and strong two. What is left out is Cl, what is left out is Na, so which you will get in this, and you will subtract this, right? As simple as that. They might also ask you degree of dissociation. That obviously is in weak compounds, so nothing. Now you have, oh god, why it's like this, yeah. Now you have this, right? They might give you, at given constant this, the thing you have to divide that by this. So this is maximum, alpha is always less than 1. Alpha is going to be always less than 1, that's what I'm trying to say. This gives free energy. Remember, delta G when negative and Kc greater than 1, then it's going to be spontaneous reaction. Sometimes they ask, delta G is negative, tell me what is the possibility for Kc? It's going to be greater than 1. Kc is greater than 1 means nothing, but just remember some equation. Where is that equation? For example, let's say this equation, not exactly this equation. Yeah, Kc is nothing but this. If it's going to be greater than 1, it means what? See, this thing is coming in numerator and this thing is coming in denominator. When we say Kc is greater than 1, it means this has to be more than this. Then only it will come equals to 1 or less than 1 or greater than 1. So greater than 1, it means this has to be more than the numerator. The denominator has to be more than the numerator. That's all it is. So spontaneous means what? Product is forming naturally. That's what is shown by this. That's what is shown. So for the spontaneous or naturally processing equation, the delta G has to be negative. Now reaction substitutes. Quickly going through all this thing. Just pause or slow it down the video and note it down. This is very summarized, but I'll show you zeroth. Then I'll show you 1 degree, then 2 second order reaction. I hope it's clear. Thermodynamics, there are a few things you should remember. They might ask you which is the intensive property and which is the extensive property. You can have a look at this superficially or whatever. To extensive property may become intensive property. Chances are there. For example, mass and volume are intensive. Once you deal with it, it becomes density and it is now extensive. Sorry, intensive. They can again ask you which one is the state function and which one is the path function. Path function on depending on the path. Internal energy. First law is nothing but the talking about conservation of energy. You might get confused with enthalpy and energy, but I'll tell you enthalpy is nothing but at the constant pressure what you get is enthalpy. Kirchhoff's equation is very important question. They might give you the 2 temperatures, they will give you the molar specific heat, they will give you the enthalpy. If you feel that question is giving you 2 enthalpies, or maybe 1 enthalpy and asking for another enthalpy, or 2 temperatures are given and similarly 1 is given and asking for another, it might hit you that it's going to be this equation. See, this heat of reaction this Hess's law, Born-Haber cycle. Born-Haber cycle, something like, you know, you go to Goa either directly, or you go to Goa from Delhi either directly, or you go to Goa from Delhi either via Rajasthan, via Mumbai, or something like that. So it's going to be the same. That's what it's saying. Doesn't matter how you're achieving the destination, but the energy is going to be not same, but you know, you can calculate the energy from both the direction. For example, you went to A, B to C directly, that's one. You went to A, then something, then B, then something, and then you went to, so you have to add all this up, and this going to be equals to what happens here. So what I was saying, and the other thing is heater formation. Oh, I don't know what the wrong, what, I'm really sorry. Okay, you should remember this. So what I was saying, this heat of reaction, Hess's law, and heat of formation usually come in one single question. Okay, and how it comes, I wish I could have told you, because of the less time I'm not able to. Heat of formation is nothing but, you know, 1 mole. When you write the reaction for this, you have to make sure in RHS you're writing 1 mole only, because we are forming 1 mole, and how much heat is involved in forming that 1 mole we are talking about. Heat of reaction is something you are consuming, right? For example, in certain reaction, you can either get H positive or H negative. If it's going to be positive, it means you have used the energy. It's going to be negative, it means you have given off the energy. So the whole reaction we are talking about the heat. Here we are forming 1 mole, and then we are talking about heat. And here we are telling 2 ways we can go through, and we can calculate both ways. Second law is nothing but they're talking about entropy. The entropy always increases if the reaction has to be spontaneous. Question type could be like this. Again, the same theme on Gibbs free energy. History always, this is going to be always spontaneous, right? This, because we want our reaction to be exothermic, that is, they should be giving off the energy, and the entropy should be increased. Here both are opposite, entropy is decreased, and even the reaction is wanting energy, so it's going to be never, we cannot fix it. This is spontaneously, always spontaneous, but this we can fix with increasing or decreasing temperature, depending on what is this, right? Because you have to be, you know, a little bit of mathematician for this, because what you increase will be, because the main goal is G, delta G has to be negative. What you can increase or decrease that will make this thing negative is what it is being shown here. Okay, we are almost come to the end. I'm not sure if this is going to come in question, and I'm even not sure what the hell is this, but I have written it out. They're talking about the enthalpy. Whenever you see delta H, it's mean enthalpy we are talking about. U is internal energy. P, it means constant pressure. For exothermic reaction, it's like this. It's actually, if you analyze these and these, are actually talking about the same thing. For the reaction, if they have given you any graph, always make sure you see what is on the x-axis, what is on the y-axis, and how it's changing. That is the main thing. Don't get scared of the graph. Yeah, this is an important question. See, I must tell you, this is somewhat equal to activation, and I don't know how to show you, but it is somewhat equal to this. Hey, not this. Wait, something is fishy. Oops. Where is the activation energy? Yeah, this one I was talking about. I don't know how to say this. See this. How do you calculate activation energy in reaction kinetics? Don't remember this formula, it's very rare. But another form for the formula is they will give you one reaction kinetics, then they will give you reaction constant. God, they'll give you one reaction constant and they will ask you activation energy. You can accordingly feed. But here they are asking about activation energy, and here they're asking about energy, but in case of enthalpy. How enthalpy? So everything is same. Everything is same, just that extra 2.303 is added here, and instead of this we have enthalpy. It's very easy to remember that Clausius-Clapeyron equation. They might ask you, it's very high chances. Remember, make sure that you take care of the units, care for the units. Okay, so just in case if they've given you pressure, two pressure, this time it's not osmotic pressure, it's pressure, normal pressure, I hope, and they will give you some boiling point. And remember, if the normal boiling point is not given with, because you need two boiling point, right? So if the pressure is, and you need two pressure, if the normal boiling point is given and there's no associated pressure, you must know that the normal boiling point is always at this pressure, 760 mmHg, or 1 atmosphere, or 760 torr. So you must know a little bit of conversion factor. Now again, the Gibbs free energy, we've already seen it, same. And the final one, oops, I'm not really sure how to calculate this, but I've written it for you. If you get it useful, just see. Third law is, they are saying that entropy of a pure crystalline substance is zero when absolute zero temperature, and they say it's hypothetical temperature. So that's all I have for now. Okay, I hope you do well. Bye.